Alright nerds, so now we're going to talk about the molecular geometry of water, and we're going to compare it to two others, and it's pretty sweet. So we're going to compare it to two hydrogen-based molecules, and that's important. Those two hydrogen-based molecules are ammonia and hydrogen sulfide. Those two molecules are roughly the same size as water and have a lot of similarities and a couple of very serious differences. So, learning goal. By the end of this, you want to be able to represent water as well as understand the structure. And if you can understand the structure, the next thing you need to be able to do is explain the implications of that structure. Now, the success criteria. By the end of this, you should be able to produce a table comparing the two ideas, or comparing the three molecules that we're going to look at. And it'll put in context a lot of the kind of magic that is water, and that's a cool thing to do. So, let's have a look at the molecules themselves. First, we have water. So, makes sense, this is where we would start. We've got oxygen, hydrogen, hydrogen. This is the electron, not the electron, this is the electrical charge dispersion model. So you see the charges here are much more, like they're much more heavily dispersed, and the charges are opposite there, because this tends to be positive area, very negative. Then we have ammonia. Ammonia, or NH3, has one nitrogen in the middle, and three hydrogens coming off. That's ammonia, not ammonium. Ammonium is a different thing altogether. And this is a stick and ball model. Then we have down here, we have this stick and ball model of hydrogen sulfide, which is H2S. And you can see he's like holding his nose like, ah. And that's because hydrogen sulfide, you know it as rotten egg gas, which is toxic and bad for you, as well as smelling gross. So here we have one sulfur in the middle with two hydrogens coming off. Now you'll notice there's a very stark difference between, say, both water and hydrogen sulfide and ammonia. Ammonia sticks out there. These two are quite similar in shape, and we'll talk about that in a second. So let's look at our Lewis dot structures, okay? What do we draw like this, right? So there's an electron, 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 electron. So 6 electrons coming from oxygen, and 1 coming from this hydrogen, and 1 coming from that hydrogen. Then we want to look at ammonia. Now ammonia has 5 electrons in the outer shell, so that means it has 5 valence electrons, that's the dots, and it takes 1 electron from each hydrogen to fulfill its octet, so give it a stable outer shell. Then hydrogen sulfide comes along, and it has also 6 electrons, like water, or like oxygen, sorry, in the outer shell. Cool. And so it's going to take 1 and 1. So from the hydrogen. So the first thing you notice is that there are some pretty serious similarities between both water and hydrogen sulfide. Now, while we're actually talking about it, you can draw this hydrogen sulfide either straight like this, or the shape of water over here. And you can draw water that shape either. I drew both, so you can see both were acceptable ways to draw it. This one here is the most accurate, but if you're in an exam situation, you might not have the space, you might have to draw it like this. But if you're asked to demonstrate the angle, this is the one for both of them. So, molecular geometry, speaking of angles. Water is a bent planar molecule, which means if you look at it, say, coming in from this way, so, perpendicular to this diagram, flat with this diagram. So if you look coming in this way, it's going to be a straight line. And this way, it's going to be a straight line. Straight line, straight line. It's only when you look above it that you see that it has that sort of bent shape. Okay, so it's a bent planar molecule. Now, it's also a polar molecule because you have the positive zone and the negative zone. Then we look at ammonia, which is a trigonal pyramid. Now, what's cool about this, so here's our one here. We see that, oh, by the way, this angle, 104.45, is really, really important. As is this distance here, which is about 1 angstrom, or 95.84 picometers. So, here we see with ammonia, it has a negative end and a positive side. So it is a polar molecule, and therefore susceptible to dipole-dipole interactions. Again, we've got an angle here of 107.3. It's not flat, it's not a planar one at all, it's a pyramid, a trigonal pyramid. Then we look at hydrogen sulfide, which is another bent planar. The angle is much narrower at 92.1, and you can see we've got a negative zone here, positive, positive, so it's a dipole-dipole. Oh, sorry, no, it's a polar molecule susceptible to dipole-dipole interactions. You'll actually notice that it is very similar to water in and of itself. Interesting point. See how these two hydrogens are closer together? but they're further away from the sulfur than the hydrogens are from the oxygen. And that's because of electronegativity, which we'll come to in a minute. Right now. So electronegativity is basically the measure of the tendency of an atom to pull electrons, a bonding pair of electrons, to it, right? And it increases as we go this way and this way, which means fluorine is the most electronegative of all elements. The noble gases are kind of weird. They don't get too involved. Oxygen is more electronegative than both sulfur and nitrogen. So if we go back, that's why we see the sulfur doesn't pull the hydrogen as close as the oxygen does, because the oxygen is more electronegative, and the distance is similar between these two. So between the hydrogens and nitrogens and the hydrogens and sulfurs, the distance is roughly the same. Anyway, so oxygen is more electronegative than sulfur, and that's why it's pulled in tighter. Now, this actually affects the phase temperatures, okay? So, water has a melting point of 0, and 100 is the boiling point. Now, really important, this is not a coincidence, the temperature scale Celsius is based on water. Like, 100 was where water, 0 is where water froze, so like, that's our start. 100 is where it's boiled, and that's our end, and we'll split it up in the middle. Ammonia they're both, melting points and boiling points are much cooler than these, like much lower. But the really interesting thing to look at, as far as I'm concerned, is if we have a look at the liquid phase. So here it's between these two distances. So here it's 100 degrees. That's massive. There are very few molecules out there that have a liquid phase of 100 degrees or even larger. It's very, very few. Water is extremely rare, and that's because of its stronger hydrogen bonding, because it's got that oxygen, which is more electronegative than anything else, so the dipole-dipole bonding is very, very strong. And again, as we said, it's with strong hydrogen bonding. Alright, I hope that made a lot of sense. If it didn't, put any questions you have in the comments below, and we'll get back to you as soon as we can. Thanks for watching. Bye now.